So in the first one, what happens to these two reactants? Really? Come on. So HCl. So when you're looking at them, remember you're looking at like what happens either to electron number or what happens to oxygen or what happens with hydrogen. Like there's a swapping or an exchange of one of those three. So when you look at this, you don't see any oxygen. They're all nonmetals, so you know it's not an ionic, but you do see the hydrogen. So what happens to HCl? So it is the chlorine of the HCl. What happens to it? So the chlorine goes from being HCl to being just chlorine. So it loses hydrogen. This is oxidized. And then when you look at the nitrogen, what happens to the nitrogen? That's where it goes. So you're really just moving, the hydrogen moves from the chlorine over to the nitrogen, changing hydrochloric acid or HCl into NH3. So this gains that hydrogen, and that is reduced. And you always identify the reactant as being oxidized or reduced. So you would say HCl is oxidized, N2 is reduced in this reaction. So it's always on the reactant side. So if you see that there's a gain of hydrogen or a loss of hydrogen, that's oxidation and reduction in a reaction. Loss of hydrogen, this is oxidation. Gain of hydrogen, this is reduction. What about the second one? What kind of reaction? What happens to C6H12O6? You look at the most sort of like the most similar molecule on the product side. So what happens to this sugar? There's kind of two things. Loses hydrogen and it gains oxygen. But both of those are what? Those are both oxidation. So you see that it loses, so it goes from H12 to H10. So that's 1. So there's a decrease in hydrogen number. But it all goes from O6 to O7. But both of those are criteria of oxidation. So the oxygen ends up being H2O, which means that it gains that hydrogen, and that would be reduced. So the C6H12O6 is oxidized, the O2 is reduced in the reaction. So if you have a gain of oxygen or a loss of oxygen, that can also be characterized as oxidation reduction. Gaining oxygen is oxidation. Losing oxygen is reduction. What about the last one? So instead of being a swapping, instead of having like two reactants, two products, and you see this swapping of oxygen or a swapping of hydrogen, this is a more reactants than products. This reaction is a synthesis reaction. And when you look at potassium, where is it on the periodic table? It's a metal. Nitrogen is on the opposite side of the zigzag line, so it's a nonmetal. So this is forming an ionic compound. So the metal always does what? Potassium with its electron, what happens to it? It always loses. So metals, they always get oxidized when forming nitrogen. On the other hand, goes from being this nonmetal to being part of the ionic compound. Nitrogen gets reduced because it gains electrons. So these are the kinds of reactions that you'll see. They're either going to be really like the single displacement, that swapping. So you'll see a hydrogen get swapped from one reactant to another. If hydrogen gets swapped, then you just identify which one's oxidized, which one's reduced. The one that loses the hydrogen gets oxidized. The one that gains the hydrogen ends up getting reduced. When looking at fuels and oxygen, like those combustion reactions, remember that fuels are always oxidized and the oxygen's always the source of it. So it is always gets reduced. And then the last example that we had with it was the forming of ionic compounds. So if you see it's a synthesis reaction, then check and make sure, is it a metal and a nonmetal? So if it's a metal and a nonmetal, the metal always gets oxidized because it's going to lose electrons. The nonmetal gets reduced because it's going to gain. The other ones that we talked about after going through that oxidation reduction, we talked about hydrolysis and condensation reactions. So this actually shows a molecule of sucrose. So sucrose is table sugar. Hydrolysis is going to do what to this? What does hydrolysis mean? Splitting into two, okay? Breaking with water is what hydrolysis means. So it will always take and split. The weakest link in this molecule is always where that oxygen is. So when you have like a chain, or if you have two molecules, if there's an oxygen spanning, that's always kind of the weakest link in the connections. So rather than it just splitting randomly anywhere, it's going to be in that link that occurs. So if we break that link, that means the oxygen is going to be hanging on one of the sugars. And what does water do? How does water stabilize that breaking? What gets added? So if this is where the oxygen is, if we break this here, what happens? How do we make that stable? What gets added to that oxygen? We now have like, if we break the connection, we now have like an empty bond, which you can't have, and then we have an oxygen with nothing on the other end. Oxygen has to have two covalent bonds. So what gets added to the oxygen? The H. So the H gets added. The hydrogen gets added here. What gets added to the other side? The OH. So that's how water can act to stabilize this breaking. So the H of water, the hydrogen gets added onto this oxygen that gets split, and then alcohol gets added to the opposite side to give those carbons their four covalent bonds, and that's going to act to separate them. So you end up with, I'm not going to draw the whole molecule out, but you end up with an alcohol now on the left side, and you end up with, oh, that one's up, an alcohol hanging down off of the right as well. So we have this up and this down, but it just acts to split them. So it'll always, like, think of the weakest link is that ether. That weakest length is where an oxygen spans a covalent bond linking molecules together. And so in a hydrolysis reaction, it's going to allow you to split it. If we went the opposite direction, what would that be called? So left to right is hydrolysis, but right to left would be a condensation reaction. Condensation reactions are how you form connections between smaller molecules. Hydrolysis is how you break them down. So those are reversible reactions. So we can have reactants becoming products. We can also have products becoming reactants in this. We'll talk more about this, especially looking at sucrose and the formation of polysaccharides, how you build really large structures in the cell. We'll talk about it again when we talk about proteins, nucleic acids, because this is really the way that things get linked together into big structures in the cell. So the last thing we stopped talking about was we were talking about like hydrogenation, partially hydrogenated vegetable oils, making margarine, such things like that. What happens when you add hydrogen to this molecule? If we hydrogenate it, what will the hydrogen do?
bond to a single bond.
So that double bond is going to get converted to a single bond. So remember that carbon always has to have 4 covalent bonds. So in this one, this carbon has 1 bond here. It has 1 bond to the hydrogen and then 2 in the double bond. So each of those have 4. So we will break one of the double bonds. So there's just a single bond remaining. And to be able to balance that, a hydrogen gets added to one side and a hydrogen gets added to the other side. So they call that hydrogenation. It's just adding hydrogen, converting a double bond to a single bond. It actually makes the molecule more stable. Double bonds are more reactive than single bonds, and so that'll be the bond that is the most sensitive, be the most apt to add hydrogen to it. Rather than splitting the molecule into pieces, it would just form a saturated or all single bond structure within the carbon chain. So we'd end up with 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So you just end up with just all single bonds. So hydrogenation converts any double bonds in a carbon chain into single bonds. So the last topic in this chapter is also an addition reaction, just like hydrogenation, except they call this one hydration. So instead of just adding hydrogen, which is really super simple, just change the double bond to a single bond, add a hydrogen to each side. With hydration, you're adding water. So you're going to add a hydrogen and an alcohol. If you're going to add a hydrogen to one side and alcohol to the other side, it will convert a double bond to a single bond. Double bonds being more reactive, it's actually more stable having all of those single bonds. There's usually some kind of catalyst that's present. This one, it's an acid, like some type of acid just to improve the breaking of that bond. So in this one, you just sort of see like the generic reaction that occurs, an H on one side and OH on the other side. But where the H and the OH end up, if it's on the hydrogen's added to the left carbon or if the hydrogen's added to the right carbon, that is actually determined by the structure of the molecule. So there was a guy, a Russian chemist, Markovnikov, that studied this his entire life. He actually ended up having a rule named after him, which so clearly he spent a lot of time looking at this. So he took organic molecules with a double bond, lots of different types, and he would add or hydrate the double bond and then measure, okay, well, where does the hydrogen get added? Where does the alcohol group get added? Is it random or is it specific? And he found that every time he did a hydration reaction, the hydrogen always was added to the carbon of the double bond that had the most hydrogens already. So if you look at this one, do you see that there is one hydrogen on this left carbon? It does not matter that there's a methyl group up here because these hydrogens are attached to that carbon, not to the double bond carbon. So you look at the carbon of the double bond and then just look at what hydrogens are directly connected to it. So this one only has 1. On the opposite side of the double bond, the right carbon has 2. So it has 2 hydrogens connected. So he found if he added water to break the double bond, the hydrogen always gets added to the side that has the most hydrogens. So he would always find the hydrogen added to this side. It would add to, in this example, it would add to the right side, and that means the alcohol group gets added to the other one. So he tried it with lots of molecules, with really big molecules, really small molecules, and found the exact same thing. So he found that if he had a molecule like this, 1, 2, 3, 4, 5, 6 carbons. It's actually 5 carbons is the longest chain, so it would be a pentane type. It's a pentene because of the double bond in there. But he found if he hydrated that, he's going to add water, which means hydrogen gets added to one side, hydroxide or the alcohol gets added to the other side. So where would the hydrogen get added in this one? To the left. And it's because this carbon has one hydrogen connected. The other carbon doesn't have any directly connected. It does not matter how further down the chain how many carbons, there is no hydrogens on this side directly connected to the carbon of the double bond. So that's all you have to look at. So just look at the double bond. Whichever one has more hydrogens, that's the side you add the hydrogen to. So he found that this is what would end up. You'd break the double bond, you'd add a hydrogen to one side, add the alcohol group to the other side, but you know which one it would go on. It would go on the left side because that's the one that has the most number of hydrogens. So that's called a hydration. So in these, here's a good one, identifying reactions with the first two as the example up here and identifying the reaction. This would be identify what is oxidized, what is reduced. So which reactant is oxidized in this first one? The magnesium. Magnesium's the metal. It always loses electrons. Loss of electrons is oxidation. So the metal always gets oxidized, and that means the chlorine, being the nonmetal, is reduced. Looking at the second one, what gets swapped in this single replacement? The oxygens. You see that the oxygen's on the copper in the first one, but on the hydrogen at the end. So it's the oxygen that's getting swapped. So what happens to copper oxide? It's going to lose oxygen, so this is reduced. Whereas the hydrogen is going to be the one that gains the oxygen, so it is oxidized. So you can call it oxidation or oxidized, either one. Call it reduction or reduced, either one. Okay, so when you look at the single replacements, look and see, okay, is there oxygen getting swapped from one reactant to another, or is there hydrogen getting swapped from one reactant to another? And that'll help you to identify if it's oxidation reduction. So in this one, what's this called? This is a what? This is a hydration reaction. Hydration, because it's adding water to the double bond. Is it done correctly? Is the hydrogen added correctly? Is the alcohol group added correctly? It doesn't matter. See that this carbon has how many hydrogens connected? 2. But then the one on the opposite side has 2 as well. So it doesn't matter. You could draw it this way, or you could add the alcohol to the left side, because remember, you could just flip this molecule back and forth. Okay, so it wouldn't matter which one you added because they have the same number of hydrogens. The only reason it would matter is if one carbon of the double bond had more hydrogens connected than the other, then you would have to choose. What's the last one called? No, we didn't break anything. We didn't break into 2. Hydrolysis would break into 2 molecules. This did what? It broke the double bond, so it is hydrogenation. We added hydrogen. So hydrogenation, or think hydrogenation. So we added hydrogen. So is that correct? Does it matter? Like, does it matter where the hydrogens are added? No, they're both hydrogens. So you're going to add a hydrogen to each carbon of the double bond. One hydrogen gets added here, one gets added here, and it changes that double bond to a single. So see how the products have 3 hydrogens around, making a saturated solution.
If it's going to be H2, is it always going to be hydrogenation?
Yes. So if it's H2O and you see it breaking a double bond, that's always going to be hydration. Okay, so we have hydration, hydrogenation, and then we have hydrolysis and condensation. So kind of list those and define how would you be able to pick them out. So that's really what you're going to see is on an exam, you may see this reaction, and I'll ask you, what kind of reaction is this? So recognizing if you're breaking a double bond, it's hydration if you're adding water, it's hydrogenation if you're adding hydrogen. And if you're breaking a molecule into two pieces using water or forming, then that's hydrolysis and condensation. All right, so that finishes up chapter 5. Not such a terrible chapter, just those things down at the very end. This takes us into chapter 6. So chapter 6 is about something that you're probably more familiar with, especially if you eat food. So carbohydrates. So the carbs is what they typically refer to them as. So in this, we're going to talk about simple carbohydrates, those simple sugars, and then we're going to talk about the polysaccharides, the really big carbohydrates, how they're different, what their bond arrangements are, and we'll relate this to a lot of the nutritional chemistry. Just the term carbohydrates, carbo means carbon, and when you hydrate, you have water. And if you look at the ratio, all carbohydrates, if they're a simple sugar or if they're a polysaccharides, all carbohydrates, for every carbon, you have H2O. So that's how that name came about, is the ratio of carbon to hydrogen and to oxygen. It's simplified, looks like there's one water for every one carbon in the molecule. So you can have monosaccharides. So mono means one, and saccharide, which is kind of like, you think of saccharin, like the artificial sweetener, it got its name because saccharide is Greek for sugar or Greek for sweet. So that's how that name was derived. Monosaccharides are single sugars, the smallest of them, whereas disaccharide, di means two, so that is two monosaccharides linked together. Those two make up the simple sugars. They're relatively small. They don't have a lot of processing when you ingest them. They get absorbed relatively fast compared to, we'll come back to these at the end, compared to the huge molecules. These are the polysaccharides. Poly means many. So mono is one, di is two. Poly means many. Polysaccharides, they say it's 10 or more monosaccharides. But in fact, most of the polysaccharides you ingest are hundreds or thousands of monosaccharides in one long chain or in one big branched complex. Okay, so they're really huge in comparison. These require a lot of processing. There's a lot of digestion that has to go on with polysaccharides before you can absorb them and use them for any nutritional value. And if you don't break them down, they won't get absorbed. They pass straight through you. That's what fiber is. So fiber or cellulose, we'll talk about that as well. So a very common polysaccharide is starch. And where do you find starch? It's from plants, and you find it in pasta, potatoes, rice, grains, breads, cereals. It's your flours, okay? So starch, commonly called flour. Whereas your simple sugars, that's table sugar, that's honey, that's your fruit sugars, okay? Very small, tend to be sweet. Is flour sweet? No, it's kind of pasty. It's because those molecules are huge. If you put some flour on your tongue, you're like, okay? It's because it's a huge molecule. You're not going to taste the sugars in it. It's combined into this really large complex and doesn't stimulate the sweet receptors from your taste buds. So we'll talk about all of these today, just to show you kind of size-wise. Monosaccharides, single ring structures. We'll first talk about them just as straight chains, but they do form rings. They need to form rings in order to be able to link together in a condensation reaction to form disaccharides. Or you need to take hundreds and thousands of these little sugars, link them together in order to form the polysaccharides. So see how that says it could be up to 10,000 little sugars linked together. Most of the ones that we ingest are hundreds to a couple of thousand. So here it is. So when you look at this one, and this is actually glucose, the most common of the monosaccharides. How many carbons? Glucose has 6. Since it has 6, they call it a hexose. So hexose means 6 carbons per sugar. So a 6-carbon sugar is a hexose. So remember that I said that carbohydrates are like 1 carbon per water. So can you see that most of the carbons have a hydrogen and an alcohol connected? So remember H and OH makes H2O. So can you see how each carbon looks like it has a water combination to it? So especially this one. Each carbon in that middle part of the chain. These, so many alcohol groups, so 5 out of 6 of the carbons have an alcohol connected, so they will call them polyalcohols. Poly again means many. And relatively, there's 1 alcohol per carbon. So remember that alcohol's got oxygen. Oxygen's electronegative. That is going to create all of these little slightly negative regions, slightly positive regions on the molecule. So sugars, small sugars like glucose, fructose, sucrose, they are soluble in water because they're polar. Lots of alcohols make these small sugars, the simple sugars, polar. So you could think like carbon number 2, slightly negative over here, slightly positive over here. Carbon 3, slightly negative, slightly positive. So remember, it makes that little zigzag kind of structure in the tetrahedral. But that means that there's going to be lots of little areas that have slight positive, slight negative, and that's going to allow sugar to interact with water. When you put it in solution, it's going to dissolve and stay mixed. Other part, this. And they'll always draw, when they draw a sugar in a straight chain, they will always put the double bonded oxygen group always at the top, okay? Whether it's on the very top carbon or on the second carbon, they always list it that way. And they always number the carbon chain starting at the end closest to that double bonded oxygen. So you notice how it's 1, 2, 3, 4, 5, 6, top to bottom. Whenever you see a straight chain, you can number a sugar chain that way. Okay, it'll always be top to bottom in the order. That top group, whenever you have a carbon double bonded to an oxygen with a hydrogen on the end, that functional group is an aldehyde. So this area, this is the aldehyde. It would always be on that first carbon. So if there's a double bonded oxygen on the first carbon, you know that's an aldehyde. So they can call glucose an aldohexose. So they will identify it as the aldehyde on the end, and it's a 6-carbon sugar. In comparison, you could have a 5-carbon sugar, so the first one is the a different aldohexose. This is not glucose. I'm not sure what sugar that is, because notice all those alcohols are all on the same side. That's a little different. But the one that's on the right side, if you count 1, 2, 3, 4, 5, there's only 5 carbons in this one. So this is like ribose or deoxyribose is this type. It's only a 5-carbon. So while 6-carbon sugars are called hexoses, 5-carbon sugars would be pentoses. Remember that hex means 6. Pent would be 5. So this side is this is a pentose. And notice the position of the double bond oxygen. So this one is on the second carbon instead of the first. When you have a double bond oxygen in the middle of a chain, that makes it a ketone. So on the end is an aldehyde. In the middle, it's going to be a ketone. It'll always be on the first carbon or the second carbon. You're only going to see it on the top one or the second one. If it's on the top one, it's an aldehyde. If it's on the second carbon, then that makes it a keto. So you would call this a keto pentose. This means a 5-carbon sugar, and there's a ketone on the second carbon. There are sugars that only have 3 carbons. They're trioses. We don't really talk about them very much. There's ones that have 4. Those would be tetroses. Most commonly, we deal with the hexose. Most of our monosaccharides that you ingest in your diet are hexoses. But like ribose and deoxyribose will mention, just because of their use in DNA and RNA, and they're pentoses, so they're just 5-carbon sugars. But that's what the name actually tells you. This will actually discriminate and tell you a little bit about the sugar. An aldohexose would be a 6-carbon sugar with an aldehyde on the first carbon. A ketopentose would be a 5-carbon sugar with a ketone always on the second carbon. So let's add one more factor into play, and this is this. One of the reasons we talked about this in chapter 4 is so that we could actually use this in describing sugar molecules. So remember chiral carbons. Definition of chiral. Chiral is only seen in carbons. Oxygens cannot be chiral. Hydrogens cannot be chiral. So you only are looking at carbons. You have to have 4 single bonds. So any carbons that have double bonds automatically get thrown out. So that means the aldehyde carbon, the ketone carbon on the sugars, you don't count those. They have to have 4 different groups attached. So that's another criteria. So I have in this one, here is this carbon. There is a methyl group on the left, a fluorine above, a chlorine below, a hydrogen to the right, 4 single bonds. All of those groups are different, so that carbon is chiral. So remember, with a chiral carbon, if you make the mirror image of the chiral carbon, you cannot lay it on top of each other. They're not identical. They will be non-superimposable mirror images, much like your hands. You can't lay your hands on top of each other and have your right identical to your left. No matter how you lay them, they won't match up exactly. So that means that you have a pair of molecules that are connected the same, but are different spatially. And that ends up creating what they call like pairs, those enantiomers. So looking at, not that one, let's just look at, this is glucose again. This is glucose. 6 carbons in the chain. It's an aldohexose. First carbon, is it chiral? Yes or no? No, why? First carbon is not, because it has a double bond, okay? Double bond, throw it out, okay? What about the one that's at the bottom, 6 carbon? 4 single bonds, is it chiral?
No.
Why?
That's too big.
Has 2 hydrogens, right? All the groups have to be different. The top and the bottom ones, they're never chiral because they always either have a double bond oxygen or they have 2 hydrogens. So the top and the bottom, it's really those middle ones that you're most interested in. So looking at 2. And the reason it's easy to see this chiral is, see, there's a hydrogen to the left and alcohol to the right. There's a single carbon group above. And remember that the whole thing below counts as the group below. So are they all different? Yeah. What about the 3rd carbon? Yep, hydrogen to the right, alcohol to the left, 2 carbon group above, 3 carbon group below. So yes. Carbon number 4? Yep. Carbon number 5? Yep. So there are 4 chiral carbons in glucose. So that means you can like swap these back and forth and make chiral carbon. You could make mirror image pairs with each one of them. You can actually make 16 enantiomers of glucose. So then they were like, well, we need to be able to define these a little bit more, because like you can't be like, well, there's all of these different kinds. So instead, they said, well, we're going to define glucose based on the lowest chiral carbon, the one that's furthest in the chain from the aldehyde. And so it's always the next to the last. So when you look at this, they said, so we're going to make the mirror image of glucose have this criteria. So here, there's the D, where is it? Here. Okay, so we're going to identify or characterize and name these sugars that have all these crazy chiral carbons. We'll draw them, they call these Fisher projections. So it's in a Fisher projection, they don't list the chiral carbons, they just put them as little crosses. So it's an easy way to pick out chiral carbons because any of the carbons missing in the chain, those ones are chiral. Okay, so those 4 are the chiral carbons, but this one, furthest from the top, is going to determine if the glucose is the D form or the L form. And the way that I remember it is it's where the alcohol is. So if the alcohol is on the right, it is the D form. If the alcohol's on the left, it's the L. And so D-glucose and L-glucose, can you see how these look like mirror images? So if you took one and looked at it in the mirror, it would look exactly like the opposite one. These are the right and left-handed versions of glucose. And they're defined according to the alcohol at the very bottom, the next to the last one, or the lowest chiral carbon in the chain. Okay, the one furthest from the aldehyde is the way that you define them. This is the only molecule that I think you should be able to draw. Okay, you don't have to draw any of the other sugars, glucose or galactose, fructose. You don't have to be able to draw any of the disaccharides, but glucose is the most common monosaccharide. D-glucose is the most common form. In fact, in nature, D sugars are the normal. There's not very many L sugars found in nature because the shape is important. And so it has evolved that the shape of the D sugars are used and processed easier. Remember how we were talking about drugs, how like one form of Tylenol and the other mirror image of it, one does nothing, the other one works fine? Well, it's the same thing in terms of the cell. The shape of D sugars fit enzymes to be able to use them for energy. And so D sugars are normally found, L sugars are actually pretty rare in nature. So how do you remember this one? So with D-glucose, just remember the aldehyde's on carbon 1 all the way at the top. So it's got a double bonded oxygen. Then you just put 6 carbons in a chain. I remember the alcohol positions. So I can remember right, left, right easier. That's just me. So I remember carbon 2 is alcohol on the right, carbon 3 alcohol on the left, carbon 4 and 5 alcohol on the right, and then the bottom one's not chiral, so it's just CH2OH. Okay, so the bottom one, you can just list it. It doesn't matter where you put the alcohol on the bottom because it spins around and it's not chiral. So it really doesn't matter with its position. But that's how I remember that. I remember right, left, right. That is the position of the alcohols on those chiral carbons for D-glucose. So for example, there's D-glucose. Look at D-galactose. It's only different by what? Carbon number what? That's the only difference. Carbon 1's identical. Carbon 2, alcohol's on the right. Carbon 3, alcohol's on the left. But carbon 4, galactose has the alcohol on the left. Glucose has it on the right. That's the only difference. So these are actually isomers of each other too. But they're very different. Galactose is actually part of milk sugar. You don't find it in other places. Glucose is found in a lot more places in comparison. Then they show you talose. I'm not sure where that one comes from. I've never heard of it before. But it is another isomer of glucose. How is it different?
2 and 4.
So 2 and 4. So it's more like, it's kind of like a mix between the two of them. We're not really going to talk about diastereomers because that's what these are. They're just that they're different ways that the alcohols can be positioned on these chiral carbons. They're all enantiomers of glucose or isomers of. So glucose, most important monosaccharide. Why? It's the most abundant found in nature. So you find glucose in grains, in regular sugars, vegetables. It's part of the disaccharides. Every disaccharide has at least one glucose. It is the building block for all of the polysaccharides. So all the starches, they're made of hundreds and thousands of glucose units. So when you think of glucose, you should think of it in terms of blood sugar. So for all animals, the sugar that's found in the blood is glucose. So in lab, we've done glucose dipsticks. We've used those dipsticks to be able to measure the amount of glucose in solution. Those dipsticks have unit values as well. And in fact, blood sugar values have a unit value. Most of the time, people don't talk about the unit value. They just talk about blood sugar as a number. Okay, so they say that my blood sugar is 80, okay, or my blood sugar is 250. That is in milligrams per deciliter. So normal is 60 to 100 milligrams of glucose per deciliter of blood. So deciliter is 100 milliliters, okay? So that's the amount. So when they do finger sticks, there is actually a unit value to blood sugar. In healthcare, so human healthcare, 30 to 40% of your patients are going to be dealing with issues of blood sugar. This may be the primary reason that you're taking care of them. This may be a secondary reason because diabetes can end up causing widespread changes in the body. Animals also come down with diabetes, have to have insulin, have to have it monitored. So we're going to talk a little about what does that mean? From the human perspective, and I have a lot of vet techs in here, but from the human perspective, this is helpful just for your own human health, okay? But then you can apply this to what it means in terms of patients you're taking care of, whether animal or human. Diabetes mellitus for humans, there's 110 million people that have diabetes in the United States. 110 million. It's the most recent number that I could get, okay? And it's increasing every year. There's two types though. Type 1 diabetes, they call it insulin-dependent diabetes mellitus. So what happens is it develops because of some malfunction or some damage to the pancreas. So your pancreas is this little organ that lays up underneath your stomach. So it's sort of right about here. It's pretty deep. And it's soft and glandular. And it secretes a hormone. The hormone is insulin. As long as insulin secretion is normal, then you can regulate blood sugar. So here's how that little picture shows you. So insulin gets secreted when your blood sugar goes above 110. So for humans, for animals it can vary, but for humans, above 110, your pancreas gets the signal, there's blood sugar higher than normal in the blood, and so insulin gets secreted. Insulin gets secreted into the blood, so it circulates in the blood, but it is capable of diffusing out into tissues. And you see in this picture, see there's on the body cell, so that little funny round looking cell, this is the body cell. And so you have trillions of these, but the body cell has what's called a receptor. And so a receptor is attached to the surface of the cell and is kind of embedded and anchored in the cell. It's kind of like a lock, okay? So it's like this little passageway. So insulin comes along and insulin fits into the receptor. That's like a signal, much like a lock and key. You can't open a locked door unless you have the key. Insulin is the key. So that receptor requires insulin to bind. That sends a signal to the cell. There's sugar in the blood. We can go ahead and take it. So that allows glucose to move into the body cell. If there's no insulin, then there's no signal. The locked door stays locked. The cell does not get the message that there's plenty of sugar in the blood, so those cells just sit there. And so your blood sugar goes up, blood sugar goes up, blood sugar goes up because there's no insulin present. So what happens is, this can happen, one, it can be genetic. So you can actually be born without a functioning pancreas, where you don't have the cells that secrete insulin. They're called beta cells. It can also happen because of a virus. So they have found that some children have viruses during childhood. The virus actually infects their beta cells and triggers damage and destruction of those cells in the pancreas that make insulin. So for whatever reason, your pancreas is not making insulin. This isn't such a big thing when you're little because you don't have a whole lot of cells. So when you're 5, 6, 7, 8, you're still a little kid. And so you're only talking about like billions of cells, not trillions of cells. The kicker comes in when you hit puberty. Because when you hit puberty, growth hormone gets secreted. And what does growth hormone tell your cells to do? To grow. Yeah. It tells your cells, we got to get big, okay? So we're going to have to increase in number. We're going to increase in height. We're going to increase bone length. We're going to increase muscle mass. Everything needs to start building. So how do early teens, what does their eating habits become like in this time? They eat everything that's not nailed down. That's what I found. So when my kids, like I would come home and an entire box of cereal would be gone. A gallon of milk would be gone every 2 days. I was like, what are you bathing in this stuff? Like, what are you doing? Like, I can't even imagine eating. I ate 3 bowls of cereal. I was hungry. You ate 3 bowls of cereal because you were hungry. Jeez. Okay. So that was like that period of time, just like right around the onset of puberty, huge amounts of growth that goes on. So that means that you're really upping cell activity. You need a lot of energy. And so those energy demands are going to require an increase in nutrients. And that's why you're like eating all the time. That's when you begin to see the issues of type 1 diabetes. Because that's when those cell energy demands, you're starting to see that blood sugar levels go up, but they're not coming back down. Blood sugar levels go up, but your cells don't get the sugar. There's no insulin secreted, and so the cells think we're starving. So body cells don't have insulin to unlock the door to pull sugar into the cells. Those doors stay shut. Blood sugar's super high in the blood, but the body cells are starving. So the body cells say, well, we're going to burn fat. And so what begins to happen to the patient that's showing symptoms of type 1 diabetes? They lose weight. So they start wasting. So you start to notice they start looking thinner. They start losing, like the baby fat starts disappearing. But then it also says, well, if we can't get all our energy from fat, we're also going to burn protein. But where is the most of your proteins? In your muscles. So you begin to see wasting too. So the patient begins to lose weight. They're eating constantly. They're losing weight, and they're also getting weaker. So you begin to notice that there's fat loss, muscle mass loss. The problem comes into play twofold. One, I wish it would stop that. One, the acids, when you burn fat, there's a byproduct, there's a waste molecule. Your kidneys have to get rid of it. The waste molecules are called keto acids. So burning fat generates these keto acids. Now, it's not a huge problem if you're also able to metabolize glucose. There are people that like do the keto diet and they ingest large amounts of fat, severely restrict the amount of carbohydrates. That's not a big deal because they're still getting nutrients from that, and they don't have this. So if you're on a keto diet, you're not eating carbs. You will never have hyperglycemia, okay? Because you're not ingesting any of those sugars or starches. But somebody that's a type 1 diabetic typically is eating a combination of carbohydrates, fats, and proteins, and the carbohydrates are getting absorbed, but there's no place for them to go. So blood sugar levels, instead of being 110, blood sugar levels begin going up, and they stay high because there is no insulin to signal the body cells to take the sugar out of the blood to bring them back down.
I get a lot of diabetics at the hospital that don't take their insulin and stuff like that. And I remember one lady, her glucose level was about 400, almost 500.
Oh, I've heard of 800. okay?
And the nurses started panicking and they had to give her steroids and everything because they thought she was going to go into shock. And just
So the way to think about hyperglycemia, and this is really, hyperglycemia is really the problem, okay? So the ketoacidosis can actually drop your blood pH. It can lead to tired, lethargic, like you can end up going into a coma from excessive acid. But the hyperglycemia is really like the underlying problem, because hyperglycemia, if you take water and you add sugar, that's kind of like your blood sugar when you eat, right? So if you eat any carbohydrates, then those sugars get absorbed and your blood sugar goes up. Well, normally insulin brings them back down till it's normal, then insulin secretion stops. That's sort of the normal process. But if not, the more and more sugar that is collected in the blood begins to make the blood thick. Think of maple syrup. Maple syrup has a lot of sugar dissolved. How does maple syrup pour compared to water? Really slow. So now you're going to put this thick blood in a tube, your blood vessel, and you're going to make your heart try to pump it. Do you think it's easier or harder? Yeah, it's harder to squeeze the syrup out of the bottle compared to squeezing water out of a bottle. So the same thing. So your heart now has got to work that much harder. That is going to increase the pressure. So thick stuff does not flow very well. So it tends to collect and increases pressure on the walls. So this is where it ends up leading to hypertension and heart disease. Hyperglycemia can create hypertension, high blood pressure, more pressure in the walls of the vessels than are normally found. And that is connected with things like stroke. Because if the pressure in the walls of the vessels get too great, they can explode. And if they explode, then that means that you're going to have internal bleeding. So you can have that. If that happens in the brain, then you end up having a major stroke. If it happens around the heart, then you end up having a heart attack. Okay, so having that thick blood is going to decrease the flow, increase the stress on the heart. Most of the time, people start feeling so terrible, they just feel so tired and so nauseous and so weak all the time, they go to the doctor because of it. And so parents will bring their 12 and 13-year-old in, they're like, I don't know what's wrong. Like, she's eating, she has no energy, she just seems kind of out of it. They can act very disoriented when there's a high level of keto acids. So they may like just kind of talk gibberish. And so you're like, I don't know what's wrong. Maybe they've like got a fever or they've got some kind of virus. Come to find out, it's because their blood sugar is very high and the keto acid levels in the blood is very high. So they treat it. The treatment for this is insulin. You have to give them external insulin. Their pancreas will not just suddenly start making insulin. So if the cells in the pancreas are damaged, they need to have insulin on a daily basis. And for many people, it's actually on a multiple times of a day basis to try and regulate it. So they bring the patient in, you put them on fluids, just try and start diluting some of the keto acids out. They put them on a low carb diet to try and bring this level back down, and they begin to give them insulin. And they give them insulin on like at least 3 to 4 times a day. So you sort of monitor your blood sugar, giving yourself insulin based on what this blood sugar value is to get it under control. So normally when you eat, do you eat the exact same thing every day? Exact same thing for breakfast, for lunch, for dinner, nothing in between? No. Okay. My dogs do. Like my dogs, it's like wonderful. They're like so much better than children because like you can give them a scoop of kibble and they're like, yay. And that's all they get. And it's like magical food to them. And you're like little brown pellets. Here you go. Okay. But my kids, if I had fed them like that, they would have been like revolt. We're not eating this. In fact, they would be like, you make this food too much. Like I would get complaints if I made the same thing too much. So we do eat. One day you might be really good and eat a salad. The next day you might go have the greasy cheeseburger and fries and a milkshake. Okay? So you do like this adjusting. So there's this constant. Your pancreas can handle it. If you don't have any kind of issues with your pancreas, you can have a candy bar and a regular soda and your blood sugar is going to go up to 160 and your pancreas is like, okay, let me just dump out some insulin. And then the body cells take up that sugar. Now some might get converted to fat, but that's the side effect of there. But it still can release enough insulin to bring your blood sugar back down. So think of somebody that's a type 1 diabetic. Every time they eat, there is some kind of glucose effect. their blood sugar is going to go up. Maybe it'll go up a lot if they eat a lot of sugar. Maybe it'll go up a little. So they're constantly trying to balance that blood sugar. They're constantly looking at the food that they're eating, calculating how much sugar is in that food, what effect it's going to have on their blood sugar, how much insulin they need to give themselves. That's a challenge. That's a challenge for a teenager, a newly diagnosed type 1 diabetic. That's a challenge for a busy 20 and 30-year-old that's like, I don't have time to sit and eat, but I took my insulin, so if I don't eat, my blood sugar is going to go too low. There is a lot of balancing that occurs, and it is not uncommon for them to have periods of time of hyperglycemia, where they ate more sugar and didn't take as much insulin as maybe they needed. So maybe their blood sugar stayed up at 150 or 200 for 4 or 5 hours. I mean, it happens. It happens. It may not be something purposeful. It may not be that, you're terrible at managing this. Sometimes it's just difficult to do with the kind of schedules that you have. Think about like your lifestyle. Sometimes you like jump up, get out of bed, you run out of the house. You're in like this panic mode because you just overslept. So it can be kind of hard to try and make sure that you regulate and monitor blood sugar and insulin injections to keep it completely balanced. But the problem comes in if you poorly manage diabetes. Hyperglycemia takes its toll. Hyperglycemia means the blood's thick, it doesn't flow well through blood vessels, and you end up with this. You can end up with capillary damage. This is most evident in the extremities because this is when it's further from the heart. So thick blood furthest from the heart is not going to come back very well. Thick blood furthest from the heart is going to kind of clog the vessels, and it can actually cause those vessels to shut down. So oftentimes people with diabetes, they complain that what do they start to notice in their hands and feet? Numbness. So they begin to lose the nerves. They get what's called neuropathy. And that is because the nerve endings have lost circulation. They're not getting enough oxygen and nutrients, so they just die back. And so then they're like, well, I just can't feel my hands or my feet. Bottom of my feet are numb. So they're walking along and they're like, I really don't even feel. It feels, my mother's described it, she said it feels like there's cardboard on the bottom of her feet. So if you cut yourself, especially in the extremities, not good blood flow, not good circulation because of this capillary damage, what happens to those wounds? They don't heal. My auntie, she got scratched by her cat, and it was like 3 weeks later, she still had this scratch. I was like, did the cat scratch you again? She's like, no, that's the same scratch. And I was like, 3 weeks later, it still looked like it had just scabbed over. Okay? Very poor wound healing. That's a big problem because what can they end up with? Infection. So those wounds don't heal, they don't knit back together and form good scar tissue, so you run the risk of infection. So then you get an infection, and most of the time infection is painful. But what do they have? Neuropathy. So what happens? They don't notice it. Okay, so they take their shoes and socks off and they're like, oh, my toe's turning colors. Okay, so they have a cut up under their foot and they hadn't actually turned their foot over in a while and looked at it. They didn't even know because they couldn't feel it. And so that wound didn't heal. Now it's infected and they haven't gone to any kind of measures to try and like clean it, put a bandage on it. They don't really even feel it. Okay, but then you run that risk of gangrene. Amputations become a bigger issue. This is why diabetics end up with these problems. Okay, so infection risk, neuropathy, there's two places in the body that you have really delicate blood vessels. One is in your eyes, the back of your eyes. If you go to the eye doctor and you get an eye exam, they either dilate your eyes and then you're like walking around like, you have to put the really dark glasses on. You're like, oh no. Or my eye doctor like actually takes this picture. Like you have to just put your eye up close to the little camera thing and it's like this bright flash. It like blinds you for a minute. So what he does is he's actually looking at the retina. Just under the retina is the nerve receptor layer in the back of the eye. Just under the retina is where all the blood vessels are that help to supply and keep those nerve endings healthy. You have more nerve endings in your eye than you have anywhere else in your body. Okay? So he looks at that. It's like red looking, but you can actually see blood vessels running through it, and that's what he's looking for. He's looking to find dark spots. In fact, sometimes eye doctors will find diabetes before a doctor will, because a patient goes in for an eye exam and they're like, I have like little funny spots sometimes when I'm in my vision, and they will actually look at this and the retina will have gray areas. Gray areas show capillary damage. Capillary damage because of high blood sugar. So areas of the retina, the blood vessels supplied to the retina, were damaged because the blood got so thick, it closed off those capillary beds and they don't grow back. So you can end up with blindness from diabetes. Your kidneys are the other one. So your kidneys are your filters. We'll talk more about kidneys and filtration in chapter 7, or next chapter. But in the kidneys, the job is that they filter out fluid waste. They filter out anything that's fluid in the body that you don't need. So like excess water, excess salts, excess waste molecules. You're born with twice as many filters as you need. So you're born really with 2 million little filters called nephrons. You only need 1 million. And that's why some people can donate kidneys. So you could donate a kidney because you'll really only need one. In fact, you can still survive with half of one. So you'd still be okay. But the problem comes into play is when the blood sugar gets really high, the blood gets really thick, it goes into those filters and it stops flowing. And that causes that filter to shut down. And again, kind of like with the retinal vessels, they don't grow back. So you can start causing chronic damage to the kidneys by not managing that blood sugar. And again, it's not always a purposeful thing. It's sometimes difficult to keep blood sugar between 60 and 120. If you don't have a functioning pancreas, this is something that really requires an awful lot of sort of mental preparation, planning, just around meals and around injections. So that's type 1. So that's the rest of your life. They are doing research with like kidney transplants, like trying to seed, not kidney transplants, pancreatic transplants, actually trying to put pancreatic cells in the abdomen and have them become functional like the pancreas. And there's been moderate amounts of hope with all of that. So maybe in the next 10 years, they'll have a really good treatment. I've seen like a robotic pancreas. So it's like a computer-controlled pancreas that actually gets implanted and it monitors your blood sugar and secretes insulin as needed. So that would be more like natural. That would be like sometimes you get a lot of insulin, sometimes you'd get a little depending on what your diet is. So they've been doing a lot of research on this because of the numbers. However, 90% of diabetics in the United States have a somewhat functioning pancreas. 90% of diabetics in the United States have what is called type 2 diabetes. Type 2 diabetes, your pancreas is still functioning, but it's not able to keep up. It's not able to keep up. It may make less insulin than what you need, but there's still some insulin, but there's a reason for it. So if your normal body weight is 150 pounds for your height, then your pancreas is supplying insulin for that 150 pounds worth of body cells. When you're 200 pounds, now your pancreas has to supply insulin for 1/3 more cells than normal weight. When you're 250 pounds, then your pancreas has to supply insulin for 2/3 more cells than your normal ideal weight. So what they find is that the higher the person's body size gets, and typically it's based on body fat percentages, you're not usually talking about just overweight. Most of the time, these are obese patients, so they're more than 25% over their ideal body weight. They may be morbidly obese, but the pancreas can't keep up. So if you're twice the size, you really then need 2 pancreases, right? Because you've got twice the number of cells. And so that's going to strain, it strains other organs, but it is going to strain the pancreas trying to keep up with insulin secretion. So the body does an interesting thing. What they found is, if you have very high body fat percentage, insulin receptors go down. But insulin receptors, remember I said are the lock. Insulin has to bind to the receptor, and that tells the cell, take in glucose. But they find that those receptors begin to disappear from body cells. So if you take this receptor and you take it away, it doesn't matter if insulin's there, it's not going to enter the body. It's not going to have an effect. So it's like having no lock. It doesn't matter if there's even a key out there. If you don't have a lock, you're not going to have very good function. This shifts the body over into fat metabolism. Because what does the body have too much of? Fat. Body fat percentage is high. And so the body is actually trying to burn fat over glucose as a way to try to bring body fat percentage down. Problem comes into play if the patient keeps eating a lot of carbs. So if the patient keeps eating a lot of sugar, keeps eating a lot of starches, keeps ingesting, there's no insulin, or there's insulin, but there's no receptors. So they end up still having issues with hyperglycemia. So you tend to see that the acidosis is less of a problem. It still may build up and still might make you feel a little crummy in terms of a type 2 diabetic. But most of the time, you start to see symptoms of the hyperglycemia. So you start to see neuropathy. You can see that this patient will have hypertension, that this patient develops heart disease, that they have poor circulation, poor healing. They can end up with kidney damage because of this. And it's all really goes back to this. So what's the treatment for that? So it's not that their pancreas is non-functional. It's that their pancreas really can't keep up with the demands of the body size. Okay? So what could you do with your diet? To what? Low carb. So if you limit carbs, then that means you would limit the amount of sugar that ends up in your blood. And what would that do for hyperglycemia? It's going to help to bring that down. So not necessarily like limit all carbs, but bring it down to kind of a low to moderate level so that it has less of an effect on blood sugar. Because blood sugar is really kind of the underlying damaging part. That's what leads to all of these vessel problems. It's what leads to all that heart problem. So they find if they put them on a lowered carbohydrate diet. Second thing, exercise will actually move glucose into muscle cells irregardless of insulin. So muscle cells will have that demand. So they have found that exercise actually helps to lower blood sugar. So lowering blood sugar through exercise, but then what else will exercise do? It's going to burn more fat, and that's going to help to lower body weight. And if we can lower body fat back down into the normal realm, then they have found receptors come back. That the body cells will actually put those receptors back, and patients don't have to take insulin. Patients don't have to take the medications to accentuate what the insulin's trying to do. All by monitoring this. Okay? Sorry. All right, so I'll quit there. I do want to talk, the only thing that we're going to finish up with is just talking about ways to monitor blood sugar. And we'll talk about A1C next time. And then we're going to move on into disaccharides and the polysaccharides next time. You should be able to finish chapter 5, the post-lecture. There's a redox dynamic study module. There's a chemical reaction dynamic study module. If you haven't done those, I'd suggest you go ahead and do those over the weekend, because we're really getting into the carbohydrate chapter 6 stuff. So I got it went all the way around good. Look around and see, there's an extra one right there. I thought I made enough, but I think I made just enough copies. All right.
My grandma, I think she has high sugar levels, like 200 and 400 as well. So I should tell her to lower her carbs.
Did she go to the doctor?
Yeah,
did
she takes
take
medication, but it's not working. So
right now,
I think she really needs to lower her carbs. She eats like rice and tortillas.
Yep, and even beans have a lot of carbs in them.
Yeah, beans.
So it's the matter of like making the salad and putting meat on it, and like
vegetables.
Meats and vegetables. Because fruit has a lot of sugar in it.
I've been doing the low carb diet, and I've lost like 15 pounds already.
Yeah.
I feel better. Like there's a lot of benefits to it, and I haven't ate like the staple food of Mexicans, like beans, rice, and tortillas.
But see, now corn is not as bad in terms of the glycemic index as like flour. So if you need to get her to just stay away from the rice and flour, bread, white bread,
Yeah,
white
bread.
potatoes, like any, they always say like just try and get her to just cut out anything white.
Yeah.
No white starchy stuff in your diet. So like even corn chips or corn tortillas would be better than a flour tortilla. If she can start that, go in that way. Just because of the so flour is so processed now that it ends up getting broken down and
enriched is
absorbed.
bad.
It's absorbed. Well, enriched just means it's got vitamins thrown in, but it's bleached. And the bleaching actually breaks the big carbohydrates, the polysaccharides, into smaller polysaccharides, so they get digested even faster. So you can find that they'll spike blood sugar, not like a soda will, but they'll still cause blood sugar to go higher than you want. Yeah, the hardest thing is trying to like get the swapping out from the whites.
Yeah.
It really is.
I was
Like the
gonna
bread, the breads,
Yeah.
the crackers,
Crackers.
chips, like, you know, like moving away from those things. Like I would say, like of all of the grains, like corn, like as long as it's like cornmeal based, like a corn tortilla.
Well, the thing you use to make the tortilla is like, it says corn flour, or not like, it's corn.
Is it cornmeal?
Yeah.
So that's ground up corn. So there is starch in that, but it is less processed than wheat flour is processed. So that is a big difference between. And it's
The only thing is she puts some flour in it too.
right to try and bring that.
Yeah.
So the other is, I don't know, I mean, when you start talking about like the way
The way
their
you
traditions,
But I
it's
feel like-
so hard.
But I feel like you could also make a tortilla without putting the flour in it. It would just be a little hard, right?
Yeah, or it's more mealy.
Yeah.
Like tamales and
Yeah,
stuff like
yeah,
that.
yeah.
Those you don't. That's just cornmeal that's been soaked. Like that would be better than having the flour
Yeah,
tortillas.
she also eats a lot of bread. But she doesn't eat fruits, because fruits have a lot of sugar in
They
it,
do.
right? But she shouldn't eat fruits though, right?
Well, things like berries and melons are not
Yeah.
bad, but bananas.
Oh, bananas, yeah, she's always eating.
No, bananas have so much. They're the highest glycemic index. It means that they spike your blood sugar more.
That's
That-
crazy.
because
Always eating bananas.
but again, it's the culture. It's a lot of that is the culture. Like that's like what you grew up doing.
Yeah, like hers would be like 200, and then some days it'll be 300 and 400.
See, but that's what you worry about. You worry about the neuropathy and the kidney damage that's going on.
But she has, she only takes the diabetes pill. She
Right,
doesn't
she
do
takes
the-
like glucophage.
Yeah.
Like she takes what she takes. It actually improves insulin binding to the receptors that she does have.
But diet would help a lot as well, right?
Yeah, I mean, my mother's type 2 diabetic, and like I've already told her all of this, and she's just like, "Don't talk to me," and I'm like, "That's fine." And then she's like, "I can't feel my feet," and I'm like,
Yeah.
"Don't talk to me." And I'm like, yeah. I go to her house and she's like, "I made all this pasta. I'll have a salad." Yeah, because I don't eat a lot of carbs either.
I've
I'm just,
stopped.
and it's the
But
same.
actually, I started what, 3 weeks ago?
Yeah.
And I was 178, and now I'm 163.
Mm-hmm.
And
But
I,
you
like,
just
I
the
feel
only
better.
thing is it has to be your lifestyle.
Yeah,
like
I'm
it
not
can't be
tired.
like
I
I'm
just-
gonna do it this week and then I'm not
Yeah.
going to for
So
3
I've
weeks
started
because
all those.
you put it back on and then some.
Yeah.
It's not. It's the thing is like you said, the carbohydrates that we have now.
Like I don't even have a
Most
longing
of
for
the
fast food anymore. I don't
but
want
the
it.
processed, pre-made, fast food,
MSG.
pre-packaged, those have been so processed that your starches are already like half digested. So when you eat those, they're going to get digested so much faster than it used to be because everything gets bleached and everything is enriched and everything. So it's been processed more. That's why a lot of people like they call it whole. So they only eat like whole grain stuff. They don't eat anything that's got any processed flours in it. You know, so that's like that whole paleo diet. They still eat carbs, but they only eat whole grain stuff. They eat whole food, so they like do more of their own cooking.
Yeah.
They don't buy stuff already made because anything that's already made has more salt in it, has more sugar in it, and has been cooked at really high temperatures to sterilize it so that they could package it and it has a longer shelf life. But then that means that it's already like half digested because of the heat. So all of those are the negative things. So that's, I mean, I don't know that like the whole keto thing is a necessary thing, but I think the limiting of processed carbohydrates, like in the
limiting
American
was-
diet, is out of control. Like just crazy. Like I had a friend, they got like a hamburger and they had like their French fries. I mean, there was like 4 cups of French fries on their plate, and I was just like, holy cow, that's like 3 potatoes right there.
Like chemistry running through.
Yeah, I know. I'm like, oh.
Let me tell you something.
Yeah, no, I can't say anything because they just look at me. Like my mother, they just look at me.
Well,
See you
have a
later.
good weekend.
Mm-hmm.